Hello, y'all. This is Darrell Lee Berry Jr. back for some more science and math. I'll be starting on the book Classical Dynamics of Particles and Systems by Thornton and Marion. So we'll be going through that, as I'll be going through that fall of this year in my fall semester at UT. So for those who've been following, I did well on my classes in the summer. I made A's. Made A in my linear algebra class, just barely, but I made it. So you can see my linear algebra videos recently. And looks like it's asking me to sign into my chat separately. One moment here. All right, so that's unusual. Let me test. Yeah, seems to be working. So I'll put a hello there. So if you're watching, be sure to chat. And I was saying that I did well on my recent classes, made an A on everything. So be sure to go to my site if you're interested in some tutoring. Like I tutor on math, science, a little bit of chemistry. I have 2 associate degrees in physics. Well, science, not specifically physics. It's just a science associate degree, but I focused on my classes in physics, as well as an associate of arts. I'm working on my bachelor's at UT, doing pretty well, and I will be going to graduate school next year. So hit me up if you're interested in some tutoring, anywhere from high school to college level, sophomore, junior level, science and astronomy. And we'll go ahead and get started on classical dynamics. Here's the cover. And we'll go ahead and get things started. Let me share my Zoom. Okay. And there we go. The size still is a bit strange. Let me try to fix that. So every time I change something, I'm still getting used to this program. Sometimes I try to resize something, but resize what I'm not necessarily intending to resize. But we got it working. So we have classical dynamics by Thornton and Marion. And we're starting at the top with chapter 1. This is the 5th edition, by the way. And so I start simply enough with the pre-stuff. Has a preface that I'll skip. All right, so we had, this was a pretty short preface. Usually the prefaces seem a whole lot longer. Well, maybe I'll come back later and read the preface. So we're in chapter 1. Chapter 1. And chapter 1 involves matrices, vectors, and vector calculus. And this is our part 1. So I'm sure I'll end up with multiple parts on these. So, introduction, and that's chapter 1, section 1. It says physical phenomena can be discussed concisely and elegantly through the use of vector methods. And it has a little asterisk there. The asterisk says Joshua Willard Gibbs, 1839 through 1903, deserves much of the credit for developing vector analysis in the early 1880s. Much of the present-day vector notation was originated by Oliver Heaviside, an English electrical engineer, and dates from about 1893. So the notation that we're using is from the late 1800s. That is awesome. So I'm always amazed at how much was developed back then. They didn't have any, supercomputers or graphing calculators, and they got so much done. In applying physical laws, and change my typeset a little bit. In applying physical laws to particular situations, the result must be independent of whether we choose a rectangular or bipolar cylindrical coordinate system. The result must also be independent of the exact choice of origin for the coordinates. All right. So we're of independent of rectangular or bipolar. I wonder why they say cylindrical coordinate system, and independent of origin choice. The use of vectors gives us this independence. A given physical law will still be correctly represented no matter which coordinate system we decide is most convenient to describe a particular system. So we can pick the most convenient one. Also, the use of vector notation provides an extremely compact method of expressing even the most complicated result. In elementary treatment of vectors, the discussion may start with the statement that a vector is a quantity that can be represented as a directed line segment. So we know a vector has magnitude and direction, and it can be represented like that. The length of the line is the magnitude, and the arrow is pointing in the direction. To be sure, this type of development will yield correct results, and it is even beneficial to impart a certain feeling for the physical nature of a vector. We assume that the reader is familiar with this type of development, but we forego the approach here because we wish to emphasize the relationship that a vector bears toward coordinates transformation. So that's the I don't know why I remember seeing linear algebra. That's because I just finished doing so much linear algebra. Vector calculus, not linear algebra. Therefore, we introduce matrices and matrix notation to describe not only the transformation, but the vector as well. So the transformation by a matrix, that is linear algebra. We introduce a type of notation that is readily adapted to the use of tensors, although we do not encounter these objects until the normal course of events require their use in Chapter 11. We do not attempt to complete exposition of vector methods. Instead, we consider only those topics necessary for a study of mechanical systems. Thus, in this chapter, we treat the fundamentals of matrix and vector algebra and vector calculus. So now we're on 1.2 already. So 1.2, concept of a scalar. Consider the array of particles shown in figure 1.1a. So figure 1.1a, so A has a y-axis and x-axis, and we have 3, 2, 1, 1, 2, 3, and each of these goes to a particular object, like so. And for B, we have apparently the same object, but in this case, y prime is that way and x prime is that way, and the objects are in the same sort of configuration, except now the coordinate system within it exists is very different, right? So that's figure 1.1 A and B. So consider A. Each particle of the array is labeled according to its mass, say in grams. So if we had 9, 8, 7, 5, 6, 3, 2, 8, 1, and 7, 4, 9, 3, 6, 5, 2, 8, 1. So let's color code a few of these. So I'm not sure how important it is that these things have moved around like this, but I guess we'll see momentarily. But I'll highlight some of them so we can see where things move to. So 4, oh, I miswrote that. And 5 is the one that's not colored. So we can see, well, it is actually the same. I mistyped the number and I thought they used a totally different matrix or something, but 7, 4, 9, 3, 6, 5, 2, 8, 1. Yeah, so it is the same. All right. The coordinate axes are shown so that we can specify a particular particle by a pair of numbers x, y. So for instance, particle 7 is at 3, 1, for example. The mass m of the particle at xy can be expressed as m xy. Thus, the mass of particle at x equals 2, y equals 3 can be written as m x equals 2, y equals 3 equals 4. Simple enough. And that's the yellow one. Now consider the axis rotated and displaced in the manner shown in B. The foreground mass is now located at x prime 4, so I guess I should say m prime equals x prime equals, oh, so let me put the numbers on the axis here. So now we still have 1, so technically this will be 1. Well, actually, they wrote the numbers in a different way as well. At least the lines connecting them. Let's see if I can get, yes. All right. So the connectors is always based upon the coordinate system. So they have one going only to this one, two hitting two. So mine is not quite as symmetric as the book one, but I'll just go ahead and make my own. You can see what it's talking about. All right. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So now M prime equals X prime. Uh, that's 4. Y prime equals 4 equals 4. So we can see that now, since we've changed the axis, the coordinate system is in. Different coordinates refer to the same exact particle. If you remember, I copy pasted this thing over here. So the distance between everything is the same. It's just the coordinate system posits 4 and 4 for the 4 particle, whereas on the other coordinate system is 2, 3. Which is simple enough. Now erase this one. And in general, M xy equals M x prime y prime. So it doesn't look like they put a prime on the M. But we just know that the two coordinates in the two different systems point to the same particle because the mass of any particle is not affected by a change in the coordinate system. So if we have a particular mass, M equals mass, the mass of the particle will always be the same. So we just have to find what coordinate system correlates the particular mass with that particularly massive particle. Quantities that are invariant of the coordinate transformation, those that obey an equation of this type, are termed scalars. So mass is a scalar. So I imagine they're going to give us a list of the scalars soon. Although we can describe the mass of a particle or the temperature or the speed relative to any coordinate system by the same number, some physical properties associated with the particle, such as the direction of motion of the particle or the direction of a force that may act on a particle, cannot be specified in such a simple manner. So scalars include mass, temperature, v, which is speed, no arrow at the top, the description of these more complicated quantities requires the use of vectors. Just as a scalar is defined as a quantity that remains invariant under coordinate transformation, a vector may also be defined in terms of transformation properties. So a scalar is invariant under transformation. We begin by considering how the coordinates of a point change when the coordinate system rotates around its origin. Right. So that's part one of this thing. Here's part two. Let's go to part three. And actually, we'll go to part three next time. So we've gotten through section 1.1, section 1.2. Coming up, either later today or tomorrow, will be section 1.3, which is coordinate transformations. So be sure to tune in and help us all understand classical dynamics. See you all next time.